Hello everyone, today in this video we are going to talk about Wheatstone bridge and its application. So Wheatstone bridge is a system of 4 resistors as you can see in the picture, and this system can be used to determine the resistance of one of the resistors. So in this picture P, Q, R, S are the 4 resistors and they are connected across the potential, and between point B and D a galvanometer is connected, and this bridge is said to be balanced when no current flows through this galvanometer. That means potential difference between B and D becomes equal. This happens when the ratio P by Q becomes equal to the ratio R by S. So now let's derive the condition. So for this I'm taking the Wheatstone bridge again with resistance P, Q, R, S, and the current I is going from here and it is dividing into two parts, I1 and I2. So and from here this I1 is dividing into two parts, Ig is going through galvanometer and I minus Ig is going through Q, and this side I2 is going through R, and out here Ig plus I2 is going through S and it's coming back. So now we'll use Kirchhoff's rule in first loop, that is ABDA. So if you use this, there is no EMF, so this 0 is equal to, now I am taking the loop in clockwise direction, so that means this current and loop is in the same direction, so this current will be positive, so this is I1P. And when you come this side, the resistance of galvanometer is G. So out here also the current and the direction of the loop is in the same direction, so this will be positive, so plus G. Now when you come to this resistance, the loop is going upward and the current is going downward, so this current will be negative, that means I2R. So I'll take the I2 this side, so I2R will be equal to I1P plus I1G. So this is equation number 1. Now I'll again use Kirchhoff's voltage rule out here, and as there is no EMF again, so I'll write 0 is equal to, so now I'll start from this G. So out here current is coming downward, my loop is going upward, so this will be negative, so this will be IgG, negative IgG. So when you come this side, it will become positive because current and direction of loop is going downwards, so this will be positive I1 minus G Q. And out here in resistance S, the current and the direction of the loop is opposite, so it will be negative I2 plus IGS. So now I'll again simplify this, I'll take I2 this side, so I2S will be equal to I1Q minus IG bracket Q plus S plus G. Now I'll put the equation together. Now when the bridge is balanced, there will be no current through galvanometer, so Ig will be 0. So I'll put Ig is equal to 0 in equation 1. So when you put Ig is equal to 0, you will get I2R is equal to I1P. Similarly, if you put Ig is equal to 0, I'm putting Ig is equal to 0 because bridge is balanced and current is not flowing through the galvanometer. So out here also Ig is 0. So now I'll simplify this. Now I'll divide equation 3 by 4. When you divide this, I2 get cancelled and I1 get cancelled. So this is R by S is equal to P by Q, and this is the balanced condition for a Wheatstone bridge. Now let us see some facts about a Wheatstone bridge. A Wheatstone bridge is said to be sensitive when it shows the large deflection in galvanometer when one of the resistor is changed by small amount. So if you change either P, Q, R, S, one resistor by small amount, there should be large deflection in the galvanometer. That time we call the Wheatstone bridge is very sensitive, and the sensitivity depends on relative magnitude of resistance, meaning the difference in their values. So the bridge is most sensitive when all the resistors are of same order, that means they are nearly equal or having same values. And it also depends on the position of battery and galvanometer. And one of the advantage of Wheatstone bridge is it's very accurate method to measure the resistance. If we calculate the resistance by Ohm's law, so we have to measure current and potential difference, and while measuring current and potential difference, lots of error will come due to the internal resistance of cell, resistance of ammeter and resistance of voltmeter. But this Wheatstone bridge works with null point method, so there will be no error due to internal resistance of cell and galvanometer. And when the Wheatstone bridge is balanced, if you interchange the position of battery and the galvanometer, there will be no effect in the balancing point. Now we will talk about application of a Wheatstone bridge. So application of Wheatstone bridge is meter bridge. Meter bridge is a device to measure unknown resistance, and it works on the principle of balanced Wheatstone bridge, that is ratio P by Q is equal to ratio R by S. So this is the picture of meter bridge, and if you compare this with a Wheatstone bridge, so we have 4 resistance out here, 1 R, S, and the resistance of this side of this wire is P, and the resistance of this side of wire is Q. So it is same as Wheatstone bridge. So constructs, it has a wire 1 meter in length, and it is made of manganese, and parallel to this we have copper strip, and we have 2 gaps out here so that we can connect resistance box out here, and out here we'll put the unknown resistance whose resistance need to be calculated. And this side we have the wire AB, and from the middle of this R and S will connect the galvanometer and the jockey, and we can move this jockey along the wire AB so that we can have a balanced bridge, and cell is connected across the wire AB. Now let's see the working. So suppose for this meter bridge, J is the balanced condition in which no current flows through the galvanometer, and the length for balance point AJ is L, and as we already know, the length of the wire is 100 centimeter. So the remaining length of remaining part, that is JB, is 100 minus L. And if sigma is the resistance per unit length, then we can write sigma is equal to resistance by length, and for resistance we can write sigma into, so resistance of the length AJ is P, I am denoting it by P, that is sigma L, and the resistance of JB is length into sigma, so length is 100 minus L, so this is 1. And the resistance from the resistance box, we are denoting it by R, and the unknown resistance, which is S, will denote it by X. Now when the bridge is balanced, we can write P by Q is equal to R by S. Now we will put the values. For P I'll write sigma L, for Q I'll write sigma 100 minus L. Sigma will get cancelled, and for S I'm writing X. So if you cross multiply this X this side, you'll bring L this side and 100 minus L to the numerator. So this is the final expression, and we already know the value of resistance from the resistance box, and we know the length, so we can easily calculate the unknown resistance by using this formula.